Hello everyone. This is in this lecture we'll be studying how we can come up the conclusion on observability of the system before we proceed to design the observer. So here we have the same system what we had in the last lecture. We have p dot equal to minus 15 p minus 15 beta plus 25 delta E plus 3 dr. So P is the basically roll rate, delta is the aileron control, and delta R is the radar control. And also we have the R dot dynamics which is function of R and beta, and delta is the control input. And also we have the beta dot dynamics where R and beta are the state variable in the dynamics. And here phi dot equal to P, and phi is the bank angle of the aircraft. This is basically lateral dynamics of the system, aircraft system. So based on the system, the question is, is aircraft observable with output vector y equal to P and R. So in the output equation only we are having P and R are the state variable which can be measured from the output equation. So if you notice here, we are having four state variable P, R, beta, and alpha, right? But if you notice in the output equation only we are having P and R. So other states are not there in the output equation. So now based on this condition, we need to check whether the system is observable or not. Similarly, we have another question, is aircraft observable with the output vector y equal to P alpha. This is, you can say, transpose. Here, similar to the above previous question number 1, here also we are having the output which is function of roll rate and bank angle. And third, so this is the second question, and third question we are having is aircraft observable with bank angle phi only. You can say being the only measured output. In the output equation only we are having bank angle. Yeah. And fourth question, here actually we are here only beta angle exists. So is aircraft observable with side slip angle beta being the only measured output. Fifth question is the observer design part. So you'll be using based on the system observability of the different questions what you have mentioned 1, 2, 3, 4. If you found to be system is observable for particular condition, we can design the full state observer. So here design full state observer for aircraft using only one of the state variables. State variables as output. Here the desired poles of the observer is given. The desired poles for observer design given to us is 1, 2 equal to -2 plus minus y is 3 equal to -16 and is 4 minus 2. So these are the poles we'll be using for designing the observer, where we'll be using this E dot naught dot equal to A minus LC E naught. This equation already you had in previous lecture, I think in lecture number 14. And so our main goal is we'll be using these desired poles to find the observer gain L, and we'll try to simulate this equation. If all the eigenvalues of this matrix are negative, then we can say if EIC, E minus LC are all negative, then E naught goes to 0 as t tends to infinity. So this is the main motivation of designing observer, right? Now we'll go to solve the problem. This solution will go step by step. So first question, is the aircraft observable with the output vector this? So our output, actually we can say x is here, x is actually we have PR beta phi, PR beta phi. So this state we are getting from solving the state equation, which is basically, we can write, this is already you had, but let me do it again. P dot R dot beta dot and phi dot, right, equal to, we have the matrix, we have the system matrix, 0 minus 15, 0, 0 minus 0.8, 1, 0, 0. The same example we had in the last lecture. 0 minus 1 minus 0.8, 0, 1, 0, 0, 0. And we have the state vector P, R, beta and phi, and we have the control vector, control matrix, which is 2.5, 3, 0, minus 3.5, 0, 0, 0, 0. So this is our B matrix, and we have delta R and delta I and delta R. So if you solve this equation, we are getting these states, right? And we are having the control input. These are the control input, which is going to propagate the dynamics, right? So now out of this state, we are taking few states as a y equal to cx. So X is coming here, and if you, based on the question, given here, we can find C, right? So now start. First question is here, question number 1. Now we can form the P matrix. Matrix for the given question 1, 1, 1, 0, 0. So 1, 1 means we are measuring. If you go back to the question, we are measuring P and R in the state vector. If you notice, we have P and R, the first 12 states. So that's why it is 1, 1. Now also you can form the observability test matrix, which is n equal to C transpose A transpose C transpose and A dash B transpose square C transpose like this. Now we can find this matrix N matrix in MATLAB. So N you can write N equal to OB is B, A and C. And if you find rank of N, and if you enter, R is found to be 3. So only P state we can measure from the observer. So one state we can't measure. So that's why we can say the system is not observable for the condition given in question 1. Now let's go to the second question. Second question is our second question is the aircraft observed with the output equation P and phi. So according to P and phi, so it will be 1, 0, 0, 1, right? So C matrix we can form C 1, 0, 0, 1. And similarly you can do the N matrix. You can find N O B S B A C, and let's find the rank. It will be rank is there, type is there. Rank A and C, and if you enter it command window, are found to be 3. Sorry, it is a type again. It will be N, rank N. So it is the value. So it is found to be 4. So in this case, we can say, since rank is 4 means number of states equal to the rank of the system 4. So it is, so we can say system is observable. Okay. So this is very important. Now we put the system is observable for the second question. Now let's go to the third part. In third part, only in the output equation we can measure phi. Phi is our bank angle. So we can form C matrix as 0, 0, 1, 0. And similarly, you can find the observed test matrix OB, SB, A, C. And we can find rank of N if you enter are found to be true. So only two states we can estimate from the observer. So system is not fully observable, not observable. Now let's go to the question number 4. In question number 4, we are having only beta available in the output equation. So if it is in the beta, so we can form the C matrix 0, 0, 1, 0. 0, 0, 1, 0. So this is actually for question number, sorry, this is actually for question 4. This is actually question number 4. Okay. Now, question number 3, only we are having 5, right? So, according to question number 3, we can, so C equal to, according to question number 3, it is 0, 0, 0, 1. And we can find N O D S V A C and rank of N is found to be R equal to 4. So we can say system is fully observable. We can observe all the states from the observer. Now we'll go to the last question. We need to design the observer. So here, let's take, since this condition is observable, so let's take the question number 3, the C matrix like this, because this is, anyway, this is observable for C 0, 0, 1, right? So now E 5. So we can, let's take the system is observable for C equal to 0, 0, 0, 1, right? So in this case, we need to design the observer gain matrix, gain vector, we can say L, right? So to find L, we need to have the desired observer folds. So V is given to us in the problem. V is here. So we can form the V vector using this desired fold location, right? So V can form as minus 2 minus 2i minus 2 plus 2i minus 16 minus 2 transpose. Now, once you have V, we can use two methods to find the observer gain. One is Ackermann, another is the place. So if you use L ACKER, Ackermann formula, we can use simply ACKER, or if you want to derive numerically, it's fine. You can go the steps what we had in the previous lectures. So here we can write A transpose C transpose and V. And if you use L place command, So we can use place command, A transpose C transpose B, and for the output from these two conditions we are having LACKER Ackermann formula. So minus 12 28 minus 28 745 3.6672 5.4 and L place we are getting the same values 12.28 minus 28.745 3.6672 5.4. So same observer gain vector we are getting for these two different commands. Now if you use this observer gain vector, we can find A minus LC, right? A is given to us, already we have. L we just found, this L will come here, and C already we have, right? So here we can use in MATLAB command ACL equal to A minus L. You can use any of the maybe this one or this one you can use. So L A C K E R multiplied by C, and now we have to use another MATLAB line where you have to find eigenvalues of CL. So if you enter it, we are getting the eigenvalues. So it is basically eigen equal to this, and we are getting minus 16, minus 2, minus 2, minus 2i, and minus 2 plus 2i, right? So if you notice, all the eigenvalues are negative, and so since all the eigenvalues are negative, we can say that E naught dot equal to A minus LC E naught. So this dynamics is stable, so it means we can say as since A minus LC EIZ are negative, E naught goes to 0 as t tends to infinity. The system is stable and we can estimate all the states. So this is the MATLAB code for this example. This you can use and you can try in MATLAB. That same thing we have done here. Whatever things we have done in this example, the same thing are given in this MATLAB code. So I am not going through this MATLAB code. You can have a look and you can try the same thing for other system as well, and you can design the observer. So let's stop it here in this part, the state feedback control observer. From next lecture onwards, we will be starting new topic on optimal control. How we can design the mathematical model, then how we can implement the optimal control methods for aircraft systems. Thank you.